In exercise 16.3, we take a look at surds and essentially figuring out which numbers are surds and how to prove whether or not they're surds by contradiction. So a surd is an irrational number. Let's highlight that before we keep going. And we represent it with a square root symbol because if we were to do a decimal place, it would not justify all the non-recurring decimals that come after the whole number. So we keep it in this square root symbol, the cube root, or the root 4 symbol to get it to the exact decimal place, okay, because it is irrational. All right. Some of the examples which are not surds includes 9, 16, square rooted, and cube root 125, and root to the power root 4 on 81. Okay, the reason being is these are all perfect squares, cubes, or quads. So here we have an example. So square root 9 gets us 3, square root 16 gets us 4, cube root 125 gets us 5, and root 4 of 81 gets us the answer of 3, which we all know these are integers and are rational numbers. Okay, so surds strictly represent irrational numbers to the maximum degree of accuracy because when we put it into decimal places, irrational numbers just keep going forever, and we can never be quite exact with rounding in decimals. So let's identify whether or not these numbers are surds. We know square root 16 is equal to, oh, that's not what we want. Square root 16 is equal to 4. Okay, so therefore it is rational and not a surd. Square root 13 gets us an irrational number, which is like 3.60555, etc., etc. So therefore, a surd. Okay. Square root 1/16. This equals 1 on 4 because the square root of 1 is 1, the square root of 16 is 4, and we know 1 on 4 is 0.25, which is a which is a number that has a fixed decimal place, okay, with 0.25 being the end of that number. So this is not a third. Not a third. Cube root 17. This gives us an irrational number. So therefore, a third. Because we get 2.5, 7, 1, 2, 8, etc., 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 non-recurring, meaning it keeps going forever without a pattern, and therefore a third. Root to the 4 of 64 is also a third because we get 2.82843, etc., etc. So this is a third with non-recurring decimals. And then lastly, here we have cube root 1728. This actually gives us an answer of 12. So not a third. All right. So anything that's an integer or a number with a recurring decimal place or a fixed decimal place, they are not surds. Anything with continuous and non-recurring decimal places, they are a surd. So the next part is, well, how do we prove a number is irrational by contradiction? So if you didn't have a calculator, how are you meant to go about figuring out whether or not a number is a surd or not? So one of the proof is what we call proof by contradiction. And the way the proof by contradiction goes is, well, if we're trying to prove that square root 2 is irrational, we have to assume that square root 2 is rational. And when we do the maths and we prove it that the rationality doesn't work, then that's how we prove that root 2 is irrational by contradiction. Okay, so the first step is we have to assume that square root 2 is rational. So we say square root 2 is a rational number, and we all know rational numbers are a ratio of whole numbers. Okay, for example, any number divided by any number. That's A and B where they're whole numbers. Okay, so in other words, integers. Okay, assume root 2 is rational, where A and B are integers. Because what do we know about rational numbers? If I have a whole number, right? If square root 2 was a rational number, meaning like an integer of sorts, or a number with a fixed decimal place or a recurring decimal place, then A and B have to be whole numbers for that to happen. You can think of any numbers that get divided by whole numbers, A and B, where B isn't 0, okay, where B does not equal 0, since that'll give us undefined, we'll always spit out a rational number. All right, for example, 5 divided by 2, if A was 5, B was 2, we get a rational number. So let's assume root 2 was a rational number. Well, then this would be the case. So here we do our linear equations. We can say, well, therefore, 2 is equal to A squared divided by B squared. And this should be equivalent if root 2 was rational. So we know it's not rational. But to prove that it's not rational, remember we're assuming it is. Confusing a little bit, but that's how we use the proof by contradiction. And so from here, let me just take this onto the next page. From here, we have to figure out either the A or the B value. So what we do is we can divide or multiply both sides by B squared, and we get 2B squared is equal to A squared. So all of a sudden we've got this issue. If root 2 was rational, we figured out A and B have to be integers essentially, okay, whole numbers. Now, we know that anytime we have A squared that has a coefficient of 2 in the B squared, or 2 times B squared, the A squared here actually has to have an even number. Like, think about it this way, right? 2 times any number, whether squared or not, is going to spit you out an even number. So let's say B here was a number 9. 2 times 9 gets us 18. Let's say B here was a number 5. 2 times 5 would get us 10. Okay, and then you, like, with it squared, it's irrelevant too. Okay, so this means A squared here, therefore A squared is even. Okay, which means A is even as well. All right, plug any number you like into B here, where it's 2 times B squared. Odd and even, it's going to spit you out an even number, which means A squared is also an even number as well. So this is super important. So we put a box around this. And this leads us to the next part of the proof. So using this logic, right, if 2 times b squared equals a squared, and we know that 2 times any number, regardless of it being positive or negative, assuming that it's an integer, is a even number, we can assume that a is even as well, because once a is squared, it's going to equal an even number that's on the left. So we can convert this and say, well, a could also be 2 times a mystery number. Okay, 2 times a mystery number, which we can call x. Okay, and we can say, well, to prove that b is even as well, because a can be 2 times any mystery number, what we have is a situation where we've got 2b squared equals 4x squared. And if we were to get b by itself, or with just a square root on top, we would have 2 times a mystery number squared using our linear equation rules. And what this says is identical to above, except the other way around. If you times any number by 2, it's always going to come out as an even number. So b here, because there's only one integer, has to be even, just like a was. So therefore b squared is even, is what this equation is saying, which is also equal to saying b is even as well. Now, here's our contradiction. If both a and b are even, okay, a divided by b are even, even number, even number, it is impossible for us to get an irrational number. Okay, when dividing. All right, so therefore we can conclude that square root 2 cannot be a rational number, because a and b here are even numbers, where a divided by b will spit us an even integer, which can't be a situation where we've got a number that's got non-recurring decimal places, okay? Because 2 even numbers divided by each other gets you another even number that's completely rational, right? And it won't have a situation where we've got recurring decimal places. And that's how you prove by contradiction. I'm hoping this makes some sort of sense. Just remember the x here is where x is any number or any integer. All right, the key here is A and B started out having to be integers, which is just a law of proving irrationality. Okay, A and B are always integers, or in other words, whole numbers. All right, let me know if you have any questions with 16.3. And that's it.